Okay, welcome back, dear students, to the tutorial about the chemical applications of group theory. And this is the part 14th video. I think this is the last video of this unit. Okay, in the last videos, we had discussed about the molecular orbital theory, and now we are moving towards the hybridization. Okay, molecular orbital theory is one of the very useful and very advanced theory. It is sufficient for explain the bonding in molecule. But we know that in a molecules like CH4 or SF6, all the bonds are identical. Okay, but in molecular orbital theory, I think you might have remembered that the electrons are in different orbitals. Okay, but even though electrons are in different orbitals in molecular orbital theory, the equivalence of bonds of these type of molecules, that BF3, CH4, SF6, like that, can be explained even with very well explained with the molecular orbital theory. If we calculate the electron densities of the electron densities, we can see that electron densities are equal. Okay, but the electrons are occupied in different molecular orbitals, like different molecular orbital, but their electron densities are equal. In that way, we can explain the equivalence of bonds. Okay, so molecular orbital theory is sufficient, but hybridization is an old concept to explain the equivalence of bonds. It also in adaptation with the symmetry of the molecule. Okay, so we can also discuss the equivalence of bonds or the bonding in terms of hybridization. Even the molecular orbital theory is a very good and a very advanced theory. We can study a little bit about the hybridization. Okay, listen. Okay, hybridization of atomic orbitals. We can apply group theory to find out various type of orbitals involved in the hybridization, provided the shape of the molecule is known. We want to know first what is the shape of molecule. Okay, then we can find out which are the orbitals involved in the hybridization. Okay, first find out the point group of the molecule. Okay, and which tell us the in what direction hybrid orbitals are distributed. Like if we know the point group, we can say in what direction these hybrid orbitals are distributed, and these hybrid orbitals are taken as the basis. Okay, these hybrid orbitals are taken as the basis vectors to evaluate the total character. Okay, that is first step is evaluate the total character using the hybrid orbitals. Okay, and these hybrid orbitals transforms as any one of the irreducible representation. Hybrid orbitals are equivalent, and we know that these hybrid orbitals are transforms as any one of the irreducible representation. And we can find out the atomic orbitals which transforms according to this IR. That is, hybrid orbitals have a particular IR. Okay, hybrid orbitals transforms of a particular irreducible representation, and we can find out the atomic orbitals having this IR. Atomic orbital belongs to this IR, because very important point is, one of the important point is, the set of atomic or hybrid orbitals of a particular symmetry can be formed only from set of atomic orbitals having same symmetry. Okay, that is the very important point is hybrid orbitals and the atomic orbital in which these hybrid orbitals formed should have same symmetry. Okay, clear? അതായത് these hybrid orbitals have a particular symmetry. Okay, and the atomic orbital in which these hybrid orbitals are formed should have the same symmetry. Okay, or the atomic orbitals forming or you involved in the hybridization and the hybrid orbitals formed will have same symmetry. That is one of the important point. Okay, first we are going to discuss about tetrahedral hybridization. We know that it belongs to tetrahedral point group. TD, point group is TD. Okay, and the hybrid orbitals are pointed towards a corners of a tetrahedron. Hybrid orbitals are point towards the corners of a regular tetrahedron. And these orbitals are designated by vectors R1, R2, R3 and R4. Okay, these hybrid orbitals, we shall denote these vectors as R1, R2, R3 and R4. That is the orbital pointing towards the corners of a tetrahedron. Okay, then using these basis vectors, that is we are taking these hybrid orbitals as the vectors and they are denoted as R1, R2, R3 and R4. And using these basis vectors, we want to find out the total character. We know that the symmetry elements of TD point group are E, C3, C2, S4 and sigma D. Okay, we want to find out the total character. We know that we have already studied that character is equal to plus or minus number of vectors retained their position. Not plus or minus. Number of vectors retain their position contribute 1. Like, okay, number of vectors retain their position and sign contribute 1. If their sign changes, they contribute minus 1. That we already know. And the number of vectors retain their position or unshifted is equal to number of vectors through which the symmetry elements pass. Okay, first point is character is equal to number of vectors unshifted. In this case, we are taking only vectors, so need not worry about the sign. We are considering only the vectors. Okay, clear. Then number of vectors retain their position or unshifted is equal to the number of vectors in which the symmetry element passing through. Okay, clear. Then we take E, identity operation. Now we know that all vectors retain their position. During E operation, all the vectors retain their position. Therefore, chi E, character of E is equal to 4. That is 4 vectors retain their position. Next is C3. Each C3 passes through one vector only. That is, this is the one C3. Okay, it passes through only one one hydrogen. That is only through one vector. That is only through one vector. So all other 3 changes their position. Only this vector retain their position. So they contribute 1. Hence character of C3, chi C3 is equal to not 4, it is wrong, it is 1. Because only one vector is retained their position. Okay, and C2. Okay, and this is the C2 axis. You can see here, this is the C2 axis. These are also C2 axis. And this C2 axis, we can see that it passing through none of the vectors. Okay, it passing through none of the vectors because, so therefore, during C2 operation, all the vectors changes their position. Therefore, chi C2 is equal to 0. Okay, and next is S4. S4 axis is collinear with C2 axis. This is S4 axis, and this S4 axis also passing through none of the vectors. Therefore, again chi is equal to 0. And then next is sigma D, pass through 2 of the vectors. Okay, and this is actually this is the sigma D plane. This plane is a sigma D plane. It passed through 2 vectors. This is vector 1 and vector 2. Therefore, number of vectors retained is equal to 2. Therefore, chi sigma D is equal to 2. So total character is equal to E 4. It is 4. Character of E is equal to 4. Then 1, 0, 0, 2. It is not an irreducible representation. By looking the character of E, it is 4, we can say that it is not an irreducible representation. It is a reducible representation, so we have to reduce it by reduction formula. Okay, and so we shall reduce the using reduction formula. I already work out here, that is NA1 is equal to, you already know the reduction formula is Li divided by H, Li divided by H, okay, chi R, okay, that's a reduction formula. So this is the character table of TD point group, therefore NA1 is equal to 1. I'm not working out, you can see simply from here, that is NA2. This is A1 representation, this is A2, and okay, NE is equal to 0, NT1 is equal to 0, NT2 is equal to 1. Okay, that you can check out easily. So hence gamma is equal to reducible representation is reduced into irreducible representation A1 and T2. That is total 4. A1 is 1 dimensional, T2 is 3 dimensional. Therefore, there are 4 irreducible representation, like 4 orbitals. Okay, A1 and T2. That is, one hybrid orbitals have A1 symmetry, and other 3, because T2 is triply degenerate, T2 is triply degenerate, therefore other 3 have T2 symmetry. Okay, one of the hybrid orbital have A1 symmetry and other 3 will have T2 symmetry. Okay, and the main point is the hybrid orbitals of these symmetries can be formed from only from atomic orbitals having same symmetry. That is, the symmetry of the hybrid orbital is A1 and T2. That is, one hybrid orbital has A1 symmetry and 3 hybrid orbital will have T2 symmetry. Therefore, the atomic orbitals should have these symmetries. That is, one atomic orbital should have A1 symmetry and other 3 should have T2 symmetry. Okay, then atomic orbitals having this A1 and T2 symmetry can be easily find out from the character table. Okay, and this is A1 representation. So x square plus y square plus z square, that is, it is s orbital. It is s orbital. Therefore, A1 symmetry belongs to atomic orbital S. S orbital belongs to A1 symmetry. Okay, next is T2. This is T2 orbital. Okay, we can see here x, y, z. We know that x represent px orbital, y represent py orbital, z represent pz orbital. Therefore, T2 symmetry, atomic orbitals having T2 symmetry, one set is px, py, pz. And another set you can see here, you can see here, that is, it is, see here, xy, xz, yz. That is, xy means a d orbitals having xy, dxy. Xz means dxz. A yz means dyz. Okay, so there are two sets of T2 orbital, px, py, pz, and dxy, dxz, dyz. Okay, therefore, sp3 orbitals, this tetrahedral orbital is either S should be must be there, because one of the orbitals should have A1 symmetry. One orbital should have A1 symmetry. So one orbital must be S. And other 3 will be a set of P, that is sp3. Okay, and another set is a set of D orbital, that is sd3 or d3s. Okay, so there are two possibilities for tetrahedral hybridization. One is sp3. Tetrahedral hybridization uses atomic orbital s and 3p, or sd3 or d3s. Okay. Okay, that is written here. The s orbital has to be definitely involved in hybridization, since there should be one orbitals with A1 symmetry. A1 symmetry has only s orbital. Therefore, s orbital must be in the hybridization, because there should be one orbital having A1 symmetry. Only s orbital have A1 symmetry. and T2 indicate triply degenerate set of orbitals. Either it be Px, Py or P and Pz, or set of dx, dxz and dyz may involve in hybridization. Hence, set of 4 tetrahedral or hybrid orbitals may be formed from 1s and 3p orbital and 1 or 1s and 3d orbitals. Okay, but from the energy consideration, it is clear that s and p orbital from same main energy level. Hence, it denoted as sp3. S and p orbital is from the same main energy level, so it is denoted as sp3. And s and d orbital can't be from the same shell. Why? Because if it is from third orbital, okay, third orbital, 3s, or we can say it from fourth orbital, 4s, 4p, and 4d, and this d and s have different energy, very much different in energy, because we know that in between this actually 5s comes. Okay, that is s and d orbital can't be from the same shell, since there will be high energy difference from the s and d orbitals of the same shell. S and d orbitals of the same shell will have high energy difference. Though so they cannot, because we know that the atomic orbitals involved in hybridization should have comparable energy. In this case of S and D, like in the same orbital they will have different energy, so it cannot be SD3. Okay, but the energies of n-1d and ns will be comparable. We already know in the lower classes that n-1d ns orbital will have comparable energy. Okay, so they can undergo hybridization, so it should be d3s. Okay, so s and p orbital, it is denoted as sp3 because they are from the same main shell. S and d orbital cannot be denoted as sd3 because they cannot be from same energy level, same level, because same S and d orbitals of the same level will have different energy. Energy will be very much different. Okay, but the d orbital from the lower level and an s orbital will have comparable energy. That is n-1d and ns orbital, we already studied that, have comparable energy. Therefore, it is hybridization denoted as d3s. Okay, and then in compounds like second period, compounds of second period like CH4 or NS4 plus, tetrahedral hybridization will be sp3. Okay, because d orbitals are available only in upper energy level. In the case of second period elements, there is no d in the valence shell or the lower level. D orbit is available only in the higher energy level, so it cannot be used. Okay, so in the case of second period compounds like CS4, NS4 plus etc., the hybridization is sp3. Okay, but in compounds like MnO4 minus, CrO4 minus, the type of hybridization is D3s. Okay, in that case we have a lower D level. In this case CH4 and NS4 plus, we don't have a lower D. We have only a higher D level. It cannot be used. Therefore, hybridization should be sp3. But in the case of MnO4 minus, CrO4 minus like compounds, there will be a lower D level is available. So the hybridization is D3s. Clear? And our next step is construction of sp3 hybrid orbitals. Okay. Now we got the tetrahedral hybridization will be sp3 or d3s. We are considering now sp3, and we want to find out what are the contributions of s and p orbital in this hybrid orbital. Okay, there is we can determine the actual hybrid orbital wave function of the actual hybrid orbital by knowing the contribution by taking a linear combination of s and p orbital, and we want to find out the coefficients. That is a contribution of each orbital towards the hybrid orbital. Okay. And this method is called inverse transformation method. Inverse transformation method. We will see later. Okay. See here, contribution of atomic orbitals to the hybrid orbitals can be expressed as a linear combination, or the hybrid orbitals are formed by the linear combination of an s orbital and 3 p orbitals. And we can write phi1, first hybrid orbital, is equal to C11s, C12px, C13py, C14py. Similarly, phi2, C21s, C22px, C23py, C24pz. Phi3 is equal to C31s, C32px, C33py, C34pz. Phi4 is equal to C41s, C42px, C43py, C44pz. We want to find out the coefficient C's. Okay. And the above equation can be written in the matrix form. Phi1, phi2, phi3, phi4 is equal to the matrix, coefficient matrix, and a unit matrix, column matrix of the atomic orbital S, Px, Py, and Pz. And this can be represented as C into S, Px, Py, Pz. Okay, and now we are doing inverse transformation. This equation can be written in the inverse form, or its inverse is, or inverse transformation is this one. Okay, the expression for inverse transformation. Okay, then it become S Px Py Pz. In the earlier equation, it was phi1, phi2, phi3, phi4. It become S Px Py Pz. Okay, this was our equation. So we are taking, in inverse transformation, we are taking this to this side and this to this side. Then coefficient will change. Okay, you can see here. That is S Px Py Pz is equal to D11. In the earlier it was C11. It is D11, D12, D13, etc. And phi1, phi2, phi3, phi4. Thus we can write D into, that is S Px Py Pz is equal to D into phi1, phi2, phi3, phi4. Okay, this D matrix is obviously the inverse of C. This D matrix is the inverse of the C matrix. And they are being orthogonal. This D matrix and C matrix are orthogonal. So, one is the transform of other. That is, C, we want to find out, what is our aim? Our aim is to find out this coefficient. That is the matrix C matrix. Okay. Symmetry. Our aim is to determine the C matrix or this coefficient. Okay. Then we are inverse transform this into this form. So we get a D matrix. From this D matrix, it is easy to find out this D matrix. I will show you. This D matrix can be easily find out. Okay, by projection operator method. Anyway, from this, if we find out the D matrix, it is easy to find out the C matrix. Our aim is to find out the C matrix. Okay, what is our aim? Our aim is to determine the coefficient of the C matrix. Okay, but C matrix cannot be determined directly. So that we are inverse transform into this form. So we get a D matrix. D matrix can be calculated. I will show you. From this D matrix, we can easily find out C matrix because they are orthogonal. So their inverse is transpose. Orthogonal, inverse of a orthogonal matrix is its transpose. That is simply we can obtain by changing the rows and columns. Okay. Then actually this D matrix is the transformation of a set of 4 equivalent basis functions of the hybrid orbitals into a set of linear combination having symmetries of the atomic orbitals. Okay, that is, this D matrix is actually the transformation of a 4 equivalent hybrid orbitals. Okay, into a set of linear combinations having symmetries of the atomic orbitals. Okay. We can easily find out the D matrix because this D matrix is the transformation of the our equivalent basis function phi 1, phi 2, phi 3 and phi 4. These are hybrid orbitals as the linear combinations of the atomic orbitals. This can easily find out from the our projection operator method. Okay, so this is a procedure to get D matrix. The procedure to get D matrix is the set of sigma orbitals on the pendant atom. We can take either the pendant atom orbital or the hybrid orbital itself. Okay, that is we can either use sigma orbital or phi orbital. Phi orbitals are the hybrid orbitals. Sigma orbitals are the orbitals of the pendant atoms. All are equivalent. Okay. Okay, so set of sigma orbitals on the pendant atom, that is this orbital. We are considering this ball as the pendant orbitals. Orbitals on the pendant atom. This is sigma 1, sigma 2, sigma 3 and sigma 4. Equivalent orbitals. Okay, we are considering that. Which have the same symmetry properties as the hybrid orbitals are transformed into SILCs. Psi 1, psi 2, psi 3 and psi 4 by using projection operator. Okay, our aim is to the set of sigma orbitals on the pendant atom which have same properties as the hybrid orbital are transformed into SILCs by using projection operator. Okay, that is our technique. To get the D matrix, we are taking the orbitals of the pendant atom sigma 1, sigma 2, sigma 3 and sigma 4 and apply projection operator to get the SILCs psi 1, psi 2, psi 3 and psi 4. Okay, these are already we had done this in the MO theory. Okay, then we get this. You know the projection operator. Projection operator. Okay, P gamma I is equal to, you already know, Li divided by H sigma R chi I R, sorry, not chi I R into R cap. Okay, from the character table of the TD point group, we have to find out P cap of these symmetries of A1. What are the symmetries of the hybrid orbital? A1 and T2. A1 and T2. Okay, so P cap A1. I'm not doing the projection operator completely. You can check out this by taking any one of the sigma orbital, taking sigma 1 or any one of the sigma orbital and doing the projection operator. We get P cap A1 is equal to 1 by 2. After normalization, we get 1 by 2 sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, you have to work it out by projection operator. Take the point character table of the TD point group and calculate projection operator for A1 symmetry. We have to work out for only for A1 and T2 because symmetries of the hybrid orbitals are A1 and T2. So P cap A1 is equal to 1 by 2 sigma 1, sigma 2, sigma 3 and sigma 4. And P cap T2, we get 3 orbitals. Okay, T2A is equal to 1 by 2 into sigma 1 plus sigma 2 plus 1 by sigma 1 minus sigma 2 plus sigma 3 minus sigma 4 and P cap T2B is equal to again 1 by 2 into sigma 1 plus sigma 2 minus sigma 3 minus sigma 4 and the last one P cap T2C, because there are 3 linear combinations, 3 SILCs having T2 symmetry because T2 is triply degenerate. Again we get 1 by 2 is the normalization constant, sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. Okay, and these are the SILCs. Okay, by doing the projection operator. Okay, that is we projects out a linear combination having a particular symmetry. First one having S symmetry. Okay, first one having symmetry of same as that of s orbital, and that is equal to 1 by 2 into sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, and px, other SILC have symmetry of px. Okay, and that is equal to 1 by 2 into sigma 1 minus sigma 2 plus sigma 3 minus sigma 4, and py, third orbital is 3, third SILC is py, have symmetry of py, that is again 1 by 2 into sigma 1 plus sigma 2 minus sigma 3 minus sigma 4, and the last SILC have symmetry same as that of PZAO, that is equal to 1 by 2 into sigma 1 minus sigma 2 minus sigma 2 minus sigma 3 plus sigma 4. This can be written in the matrix form, that is we can write as px py pz is equal to this is equal to 1 by 2 1 by 2 1 by 2 1 by 2, and the other row is 1 by 2 minus 1 by 2 1 by 2 minus 1 by 2, third row 1 by 2 1 by 2 minus 1 by 2 minus 1 by 2, fourth row 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2, and this is equal to sigma 1, we can write sigma 1 sigma 2 sigma 3 sigma 4. It is same as that of phi 1 phi 2 phi 3 phi 4, because the symmetries of the sigma 1 sigma 2 sigma 3 sigma 4 is same as that of equivalent to phi 1 phi 2 phi 3 phi 4 as our hybrid orbital. Sigma 1 sigma 2 sigma 3 sigma 4 are the pendant orbital. It has same symmetry as that of the hybrid orbital phi 1 phi 2 phi 3, so we can write phi 1 phi 2 phi 3 phi 4. Okay, so this is the D matrix. Okay, so to get the C matrix, we can inverse transform it. Okay, so we get this equation, that is the other equation on inverse transformation. We get phi 1 phi 2 phi 3 phi 4 is equal to take the inverse of the earlier matrix, that is D matrix, that is equal to 1 by 2 1 by 2 1 by 2 1 by 2. Here it is 1 by 2 minus 1 by 2 1 by 2 minus 1 by 2 1 by 2 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2, and here it is equal to S px py and pz. Okay, we can write here S px py pz. Okay, so our our hybrid orbital is phi 1. We can write phi 1 is equal to, by multiplying this matrix with this column matrix, we get 1 by 2s plus 1 by 2 px plus 1 by 2 py plus 1 by 2 pz. Okay, that is phi 1, first hybrid orbital. Second one, phi 2 is equal to again 1 by 2s plus minus 1 by 2 px, next plus 1 by 2 py, next minus 1 by 2 pz, and third hybrid orbital phi 3 is equal to here 1 by 2s plus 1 by 2 px, and third one minus 1 by 2 py, and fourth one minus 1 by 2 pz, and the last one phi 4 is equal to 1 by 2s, next is minus 1 by 2 px, third one is minus 1 by 2 py, fourth one is plus 1 by 2 pz. These are our hybrid orbitals, and this is the inverse transformation method to get the coefficients of the linear combination to get the actual hybrid orbitals. Okay, clear? And this is the end of this class. You read the textbook very well. Okay, similar way we can find out the hybrid orbitals of the sp3 or the trigonal planar hybridization and their SALCs. Okay, you work it out. Okay, we are stopping here. Thank you.